In last class we have seen something about in last lecture about center of mass. Now today we are going to see something called cross product. After this I will explain something. Take down cross product of two vectors. See what does it mean. Suppose you have any vector quantity A and you have another vector quantity B. So when you will do cross product of this A and B, then this will go in this direction. So if you are taking this direction, it means you are calculating A cross B. But suppose you have to calculate B cross A. In that way you will come like this in this direction. Now why this direction is important? Because it is a cross product. Cross product is also known as vector product. Now why do we call them as vector product? Because whenever you do cross product, your final answer is further going to be a vector quantity. Whenever you do cross product, your final answer is going to be a vector quantity. So if your answer is vector quantity, then definitely that vector will be having direction. So if you do this A cross B, then direction will be upward. Okay, now to find out direction of the new quantity, so you mention here to find out the direction of A cross B, they are vectors, so I am putting arrow like this, or B cross A, we use, there is something called screw rule. Screw rule. What is this rule? See, A cross B means you put screw here like this, and you turn the screw from A to B, like A cross B, like see how I am turning. So in that case, where the screw is going, no doubt that when we do a screw like this, screw will go upward direction. So this direction will become the direction of new vector A cross B. But just opposite, if you will do B cross A, suppose you have one vector here A and one vector here B, and you are keeping your screw here like this. Okay, now suppose you are doing for B cross A, then you will turn your screw like this, it means like this. In that case your screw will come out like this. It means what? This is your direction of B cross A. Okay, now why this concept is important in physics suddenly? Because in physics there is some concept of torque, there is some concept of your angular velocity and linear velocity. So those velocities are actually connected with the help of vector product. Okay, so immediately you mention here, now you just mention, because now we have velocity, so you write down like this, linear velocity that I'm mentioning as V is equal to, then you have to write here angular velocity, that symbol is omega. This you will cross with, now when you are making this cross product, another vector must come here, so then you will write radius vector. I don't have proper space here, you mention here radius vector R. Okay, so all the three velocities, so you can write a fresh equation like this, V is equal to omega cross R. Okay, V is equal to omega cross R. So this V is equal to omega cross R you can open again, and when you will open them you will be finding out the relation in terms of sine theta. We know that how it works in terms of dot product and cross product. Okay, and very similar concept we will also follow when we are going to discuss torque, but before that let's copy down this. So now you understand, because angular velocity will be changing, because every time angle is being changed, So there will be one acceleration coming because of change in angular velocity. So that acceleration we call as angular acceleration. So you take down another heading as angular acceleration. What is this? See here, you will give symbol alpha and definitely you'll put arrow. Yeah, you'll put arrow also, and you'll give symbol like this: alpha is equal to d omega by dt. Okay, this is vector quantity, means change in angular velocity by time taken. You will write like this: change in angular velocity by time taken. Now let's understand. Let's compare this with linear motion. Comparing this with linear motion, what does it mean? Actually, see, in linear motion, when you have acceleration, that acceleration is nothing but dv by dt. So we have three equations of motion: v is equal to u plus at, s is equal to ut plus half at square, v square is equal to u square plus 2as. Here your u is your initial speed, v is your final speed, and your a is acceleration. Because of acceleration only your speeds are not same, they are changing. And your s is when there is speed, object will cover some distance, so this s is nothing but the distance, and t is nothing but the time taken. Which time? When your speed is changing from v to u, u to v, how much time is being consumed in this change, or when your object is covering s distance, then how much time. So that is the time. And a is acceleration. If your velocity is increasing, then this is known as acceleration. If your velocity is decreasing, then it is known as retardation, right? In similar way, in case of angular motion, same concept you will copy. You will write this as, first you will write the notation: omega 1 is going to be your initial angular velocity, initial angular velocity. Omega 2 is going to be final angular velocity. Now see, it depends on the book and the professors and teachers. Some professors and teachers, they write omega I for initial and omega f for final. Some teachers write omega naught for initial and omega for final. Okay, we are going to follow 1 and 2 because it is more usual. So according to this formula, exactly we are going to write down our rotational velocity equation. So this is your final speed. So omega 2 is equal to omega 1 plus, here you are going to put alpha, because this time our acceleration is angular acceleration. So alpha, and time t. Time is same. Time is not linear or angular. Time is time because it is a scalar quantity. In same way, we are going to discuss s now. In this case, s you will replace with theta, because in linear motion we cover distance, but in angular motion we cover angle. So that's why your theta is equal to omega 1 t plus half alpha t square. Then you will write omega 2 square is equal to omega 1 square plus 2 alpha theta. Did you understand everything? Now you also take care of units. So in case of units, I am using this space. Actually, omega is nothing but angle per second, so radian per second, and alpha is nothing but radian square per second. And same, your time will be having same unit, and theta is going to be in radian, time is second. So only these many variables we are using. Now because your omega is of two types, omega 1 and omega 2, so both will be having same radian per second. Acceleration is only one, theta is there, time is there in second. Let's go ahead. Now let's understand the concept of torque. Very important concept of torque. Many students in 11th class, after studying 11th class, they forget this concept of torque completely, because they don't use that kind of numericals, they don't face that kind of numericals or physical discussion about torque. That's why they used to forget torques. So let's revise this torque, let's complete this torque in detail. So first understand what is torque. See, in your linear physics, when we decide that, now let's compare with linear physics, because if we compare with linear physics, it used to be more easy. In linear physics, when you have any object and this object is accelerating and mass of object is m, then we define a quantity that we call as force, and then that force we give with the formula ma. Exactly same thing in rotational physics. When there is a mass and this mass is rotating, so rotating symbol you put like this, means you just put this kind of any mass, and it is now suppose revolving with any acceleration alpha. But this time mass we replace with moment of inertia. Okay, like a we replace with alpha, mass replace with moment of inertia. Don't worry, I will explain moment of inertia in detail, okay, in this lecture or in upcoming lectures. Then actually with the help of these two quantities, we used to collect one more quantity, and that quantity we call as torque. And let's understand how the torque acts and what is the role of the torque. Actually, torque we say as moment of force. So first of all, the torque point you write down. First thing, it is moment of force. The very first thing, moment of force. See, when force is acting, any object can accelerate in linear direction. But when torque is acting, then any particle will start rotation. Okay, so it helps to rotate the particle. Okay, so there is difference between force and torque. Force means when you will apply the force, it is responsible for linear motion, but when you apply the torque, it is responsible for this kind of motion. Okay, now just an example. Suppose there is any particle and this particle is about to rotate like this. So first of all you find out, okay, you do one thing. This particle you connect with any kind of hook like this, and about this hook this particle will rotate like this, like this. So this particle will be having a particular, you will apply a particular force here on this particle. So direction of force will be this, you apply the force, and from this hook at how much distance you are applying the force, that distance you will put r. Get the logic slowly. So you are going to develop a torque, then how, in which direction your torque will be. So imagine you are applying your force in, see, I am giving you axis system. This is your x-axis system, and this is your y-axis system, and this is your z-axis system. So imagine you have applied force in y direction and distance is in x direction. So distance you will put r value, force will put f value. So your torque you will achieve in z direction, like this, z direction. Okay, so torque value you put tau will be the torque. Okay, so you can first you make sure about directions. Direction is very, very important. Direction wise we will go. Okay, direction wise clear. Now because this type of diagram can be confusing, so I will give you a physical part, like how physically you can understand this. But before that, you take down the formula of torque in terms of this. So this torque is equal to, no, actually you are right, F into R, but F into R is not the right formula. Actually R cross F. R cross F is the correct formula. R cross F. No, they are not same. No, they are not same. Just now I have told you, you see here, just now I have told you that A cross B will be in this direction, but B cross A you can see in downward direction. It means if you compare tau formula as R cross F, then it will look like RF sine theta. So this is the scalar answer, the magnitude you are seeing. again if you write tau is equal to f cross r, okay, it will be like f r sine theta. But see here, this formula is wrong, second formula is wrong. Why second formula is wrong? Because in second formula, magnitude wise you are getting the same answer when you multiply rf sine theta or fr sine theta, okay. But problem is direction. R cross f will be having different direction and f cross r will be having different direction. So that's why I have given you this diagram, where I will draw this diagram again. Then you will realize, okay, what is the main difference, why it is very important. So now see, you take like this. Suppose this is a tire, any tire or wheel or something, and here you have a spindle. Okay, this spindle is hinged here, and suppose there is one small something, and with the help of that one object is here. Now in this y direction you are applying your force, okay, and in this x direction you have this location of this is clear. So because r vector is very clear, that is position of the particle with respect to the origin, and they are at 90 degree, no doubt here, like here they are at 90 degree, correct. So r and f clear. Now when you will apply the force f, then this guy will start rotation, so torque will come into picture. So where will be the direction of torque? The direction of torque will be in z direction, like this, z direction, like this. In this direction you will be having tau. Why? Because tau is equal to r cross f, okay. Tau is equal to r cross f. What does it mean? Meaning is, these two vectors are giving you another vector with the help of vector product, so that vector should also have its very clear direction. That direction you will find out with the help of the concept of screw rule, a cross b or b cross a. So here make sure a cross b and b cross a, they are not in same direction. Is it clear? Actually in some textbooks or in some like professors or someone can teach you like this: tau is equal to d cross f, tau is equal to x cross f. But their intention of these variables of d and x is like to show you that from the hinge point, at how much distance your object is located. What is the meaning of hinge point? Like about which point your object is rotating, that we call as hinge point. After that you can open this, so it will look like fr sine theta or rf sine theta. In scalar format, order does not matter, who is coming first, r is coming first or f is coming first, sine theta, this doesn't matter, okay. So now we'll go ahead. So I'm changing the page. See now here, actually if you compare linear physics again, so in linear physics, when you are make sure that you have your mass, and that mass is moving with any velocity, so multiplication of mass into velocity gives you moment, okay. So sorry, momentum. So that momentum we call as p, and p momentum is nothing but mass into velocity. Now see here, this mass used to be a scalar property, but velocity used to be vector property. So the product will be a vector property, but the multiplication is a simple multiplication. Now you come to the rotational physics. What happens in rotational physics? In rotational physics, we are going to discuss angular momentum, and actually angular momentum, first line you will say it is moment of momentum. Moment of momentum, what does it mean? Angular momentum symbol, your heading is angular momentum. Actually angular momentum is your new topic. Now symbol is capital L. So this capital L is vector quantity, and moment means you are going to multiply r cross momentum is p, so momentum is p here, okay. So this is your angular momentum, and when you do r cross p, this property becomes moment of momentum, and it will be happening about a particular axis of rotation. So what does it mean? Meaning is, suppose this is the line and some object is revolving around this, like this, okay. So at how much distance that object is tied, so that distance you will put in this direction, and In which direction it is having velocity? In this direction it is having velocity. So velocity multiply with mass will be getting direction of moment. So now we are clear with direction of r and direction of p. So we can clearly see angular momentum direction will be exactly perpendicular, right? So now we are sure, we are very clear now in which direction the capital L will come. Always r cross p will come in this direction, right? Clear. Copy down this. Now actually similar, there is something called geometrically how will you define angular momentum. So actually what happens, I'll change the page. See, when anything is revolving around something, suppose object is here in the beginning and then object is coming here, then geometrically, actually this concept is very popular when we solve our like orbital mechanics problem. In like in space, all the planets are revolving around some stars and something. So there these kind of we used to see during when we study Kepler's law and all. So that time we used to discuss angular momentum. And anyway, no need to discuss right now that thing. You just mention here one special statement. Take down the statement. Geometrically, the angular momentum, that is capital L, of a particle is equal to twice the product of its mass and the aerial velocity. Now what is this, like mass and aerial velocity? Mass and aerial velocity, so you should know that mass means m and aerial velocity is dA by dt. What does it mean? Meaning is, when object is here, suppose from here object is started, suppose object is reaching here, so object is covering this much area on the path, so sweeped out area. So how much area, like with respect to this object, this with respect to this point object is rotating, like when object will complete its path, suppose object is completing this path like this, then like this, then like this, and reaching here, right? So it's like this became the path of the particle. So like in a particular time object is going to sweep this area, then again object will sweep this way, this area. So for that, according to area based, we can find out our this thing. So in 11th class physics, this concept is mentioned actually, that L is equal to 2 times mass into dA by dt. But its huge application we see in orbital mechanics, is space dynamics, in astrophysics, in aeronautic, in aerospace department. This equation comes. Copy down this. No, not area. We have to do this aerial velocity. Aerial velocity. I forgot to write this L here. It is aerial velocity. Like how much area is being swept out per second. And don't be confused. This area is not the area of the particle. No. It is not coming from the diameter of pi by... No. Yeah, how much area is being swept out here. Suppose this is Earth and this is Sun. Okay. This is Earth, this is Sun. Now we are going to understand, I am changing the page. There is a relation between torque and angular momentum. Relation between torque and angular momentum. Write down. But see, this relation is in terms of torque and angular momentum. Torque symbol is tau, angular momentum symbol is capital L. So whenever you are being confused, you understand in this way. In linear physics, torque means force and angular momentum means normal momentum, linear momentum. So whenever you divide momentum by time, or you say in Newton's second law, this is what we used to write down, dp by dt. So according to this concept, exactly same concept you can copy in rotational physics, like tau is equal to dl by dt. This guy is vector, this guy is vector. Okay, so this is the final expressions what relates between tau and l. Copy down this fast. Okay, now so understand one logic, like if there is a particle, on this particle, if there is no external force acting, then definitely whatever is if there is no external force, then there is no acceleration, and if there is no acceleration, then velocity will not change. If velocity will not change, means speed is constant, and if speed is constant, means your momentum is also constant, because momentum is mass into velocity. So if speed is constant, means velocity is constant, because I'm considering no change in velocity, so that's why your acceleration is constant, acceleration is 0, that's why your force is not acting. Like, this hierarchy is very simple. If force is not acting, then acceleration will be 0, and if acceleration is 0, velocity will not change. It means what? Speed will be constant, and if speed is constant, then because of speed multiply with mass, your momentum will be constant. Now same logic will apply. Before that, you understand, suppose there is a planet, sun is there, okay, and any planet is revolving around the sun. Now what is the main key comes here? Point is, what about the angular momentum of this planet revolving around the sun? Whether the angular momentum will be constant, conserve, remain same, or not, increment. So for that, if any extra torque you will apply on this planet, in that case angular momentum will not be constant. But actually all the giant or small particles revolving around sun, they are revolving with constant conserved angular momentum, because no one is going to push them further, no one is going to give extra torque to them. Okay, so for that you take down one important point here itself. I'm changing the page. Take down points. If no net external torque acts on a system, then total angular momentum of the system remains constant. And mathematically you can mention, if tau external is equal to 0, then like angular momentum is going to be same, whatever momentum is there, you add all together, L1, L2, L3, dot, whatever they are, everything is going to be a constant. Okay, copy this. So now we have sudden taste change. This kind of axis of rotation we will understand. Axis of rotation. So for axis of rotation, you understand first. Suppose you have a cylinder. So this cylinder can rotate with respect to this line. Okay, it means after some time cylinder will come this side. Okay, this is one case. And another case is like you have a cylinder like this, but it may revolve about this point, about this axis, so here. Okay, or another case is you have a cylinder like this, and about this point, about this line it is rotating. So in this case, after some time, your cylinder will become like this, right? This kind of rotation. So whenever there is a rotation, definitely it will be happening about axis. Okay, so whatever axis we know for the rotation, that we will come to know after seeing the motion, like, okay, what kind of rotational motion is happening. Okay, now I'll give you one more example. Suppose there is a pole. Okay, there is a pole. Suppose this pole, and one small kid is holding the pole by its one hand, and it is running in this direction like this. It is like revolving like this. So this time this kit is revolving around the pole. So this pole axis became axis of rotation. But if this kid will revolve about its own axis, that time rotation is different. Okay, axis of rotation is different. It means we have to understand exactly where is our axis of rotation, because it is going to play very important role, because actually we are going to cover two important theorems, perpendicular axis theorem and parallel axis theorem. So these are like very important theorems. So that's why axis of rotation is important. So before going to this theorem, we will also understand some more things about axis of rotation. So I will change the page. So okay, first you draw this diagram. Now we are going to understand one very important point, where we are going to understand what is called moment of inertia. Moment of inertia. And after that we will go for parallel axis theorem and perpendicular axis theorem. But before going to the details of these theorems, we should feel what is moment of inertia. So understand this in this way. Suppose there is one very heavy cylinder which is like this, and this cylinder we have, it is hinged on a support, and this cylinder is free to rotate in this direction, but there is no rotation till now. Like if you will apply some force, you can start the rotation in the cylinder. And suppose everything is same, whatever friction quality is here, same friction quality, I am going to make one more cylinder. But this cylinder I am going to make very slim cylinder like this, very slim cylinder. Everything is same, friction, oiling, or like how much oil I have put for the friction, like everything is same. Now suppose one person is, and they both are solid cylinders. Suppose there is one person, and this person is trying to rotate this cylinder, and then it is trying to rotate this cylinder. Then what do you think? In which case this person will feel more effort, in case 1 or in case 2? So actually, if you want to produce rotation in the first case, here you have to apply more effort, and here you can apply less effort to produce the rotation. So in case of case 1, so that effort what I was talking, like how much effort you will apply in this or how much, so that property is like to start the rotation, to stop the rotation, we have to define some property which will take care of that particular thing. So that property we call as moment of inertia. It means what? If moment of inertia of any object is high, then it will be difficult to rotate the object. But if moment of inertia is high, then one more problem is there. Once something is rotating, then it will be difficult to stop that thing if moment of inertia is high. So both advantages are there. Okay, or you can say disadvantage, whatever, depends on need. Okay, so you mention here masses, or you just mention here objects with high moment of inertia are difficult to start and stop the rotation. Copy down this. Then you mention at the bottom, this is the physical feel. This is the physical feel of moment of inertia. Now see, I am giving you a case. I am changing the page. You also mention this. This is the physical feel of moment of inertia. Now take down one very good example. Suppose someone is sitting somewhere, and it is very hot weather, and you have one rectangular object. Okay, and this object you can rotate about this also, and this object you can rotate about this also. Okay, so in which case that will be easier to rotate the object, and in which case it will be difficult to rotate the object. According to that only you will hold your hand. I mean, either you will hold hand here and you will rotate the object like this, or you will hold your hand here to rotate the object like this. So if you know the idea of moment of inertia, then only you will apply less effort. Otherwise, because you are going to rotate the blade or rotate the part manually by using own hand, by using own effort. So that's why a game of moment of inertia is very, very important to know. So now let's start with basics of moment of inertia. Very, very basics of moment of inertia. So first point you mention here. Okay, one type of moment of inertia is, okay, you mention here in point 1, moment of inertia is based on mass distribution, and we have also moment of inertia based on area distribution. Moment of inertia based on area distribution. In both the cases, suppose this is the axis of rotation, this is the length, and you have any mass here. If I am saying any mass is here, then when it will rotate, then its moment of inertia I, you will say as mr square if radiuses are. But if your mass is m here, but this time it is not mass, this time I am saying it is area A, so r, so that time your I will be equal to ar square. So two types of moment of inertias we used to discuss in physics, or you can say in engineering. Okay, one is based on mass, one is based on area. So currently, currently whatever chapter we are going through, whatever lectures we are going through, in future in detail you will study this in those part of machines where machines are revolving, or where parts are revolving, or in case of space dynamics, orbital mechanics, astrophysics, their particles are, you know, I hope you understand. So this mass one will help you, sometimes area one will help you. So according to the use, we will be using our moment of inertia concept. But in both the cases, either you use mass one or you use area one, your main concept of these two theorems, what I started discussing here, parallel and perpendicular, these two discussions are going to be same in both the cases. So I am going to take moment of inertia what is designed for 11th class mechanics. Okay, so which is based on mass. So I'm changing the page now. Take down in this way. Suppose you have your axis of rotation, and imagine any imaginary line. On this line, any object of mass m is going to rotate. So suppose this mass is m, so, and you also consider this is circular path, so radius r, and everywhere radius will be same. So right now your I value, means moment of inertia value, will be mr square. This is the most fundamental idea behind moment of inertia, and all other particles, all other shapes, moment of inertias are based on this concept only. Now imagine what will happen if this mass I will consider m1 and I will add one more mass here as m2. In that case, what will happen? Both the masses are revolving around same axis, right? That's why your moment of inertia of this entire system will increase. So new time it will be like m1 r square plus m2 r square, or you can say m1 plus m2 r square. Means what? You see, mass got added, right? Now imagine if I have one mass here, one mass here, one mass here, one mass here, one mass here. Means what I'm trying to say, if I am connecting them, then I'll be getting a ring, ring. If all the masses I am attaching here, then I will be getting a ring, correct? So whatever is the total mass of the ring, that mass I will replace here. So we got our first very basic concept, moment of inertia for ring. This is nothing but mr square. So what is r here? R is the radius, and what is m here? M is the mass of ring. Okay, mass of ring. Okay, copy this fast.